In the realm of modern technology, we decided to look at portable phone chargers, especially those that were solar charged, and decided that we could improve on their efficiency by adding mechanical actuation for the solar panels. We already had solar tracking idea from earlier in the semester and decided to make it even more accurate and track in real time.
This is our dual axis solar charger. It works here by taking input from 6 photoresistors. We have 2 at 90 degrees, 2 at 60, and 2 at 30 with the separations in between. When a shadow's cast over one, it'll adjust either up or down or left or right to make sure the sun is hitting it. And then it'll adjust the panels based on the angle and the rotation that it needs to be at. From the photoresistor's input, we move 2 servo motors, one for the vertical and one for the horizontal movement. It'll first do horizontal and then do vertical. From the panels, we've got 6-volt power coming into our battery charger. This acts as like the solar controller. That'll charge our 6-volt power bank, which is lithium-ion rechargeable batteries. From there, we can take it to a converter, which takes anything from 24 to 6 volts and steps it down to 5, so you can charge appliances like your phone. This is a switch just turning it on and off. It should be noted that we are running the servo motors in the Arduino with external power right now, but we can take power from the system in future iterations and use it to run the entire system as well, just like branching power off of our converter back to the microcontroller.
For the wiring diagram, we have a fairly simple setup. To all of the analog pins, there is one photoresistor each connected in parallel with a 1 kilo ohm resistor as a voltage splitter. Also, on the digital pins, we have 2 servos connected for horizontal and vertical tilt on the solar panels. Also, we have a voltage regulator connected to the ground to ensure the 6 volts coming out of the solar panels does not blow out the 5-volt USB charger.
Alright, so for the code flowchart, we start at the top. First we configure the pins and initialize the variables and servo angle, and then we read photoresistor values and calculate the averages. Next we're going to check if the photoresistor values are equalized or if the servo needs to be moved. If it's not equalized, we're going to move the bottom servo until each side reads the same values. If it is equalized, we're going to look at both sets of photoresistors, all 3 sets. We're going to compare sets 1 and 2. If set 1 is higher than set 2, we're going to map the servo angle of the top servo between 90 and 60 degrees. If it's not, we're going to map it between 60 and 90 degrees. For set 2 and set 3, if set 2 is bigger, we're going to map the difference between 60 and 30 degrees. If set 2 is smaller than set 3, we're going to map it between 30 and 60 degrees. And then after all of those, we're going to go back and see if we need to adjust the bottom servo anymore. All right, now on to the code snippets. So after we've initialized the variables and configured the pins, we're going to read the photoresistor values to each of the 6 photoresistors, and then we're going to calculate the weighted averages for each set of photoresistors and the average of each side, the left and right side. For the horizontal tracking, we're going to see if the photoresistors are equalized, which means the left side equals the right side. In order to do that, we're going to take the difference of the left side and right side. If that difference is negative, we're going to move the system to the left. If it's positive, we're going to move it to the right. And then we're going to limit the servo angle from 0 to 180 degrees, so we won't go past that. If it goes past 0 or 180, we're going to say that the system is equalized, so it's going to stop moving. And then if the photoresistor values are within 10 units of each other, we're also going to say it's equalized and stop the horizontal tracking. All right, now for the vertical tracking, we're going to see if the average of set 1 is bigger than the average of set 2. And if it is, we're going to take the difference and map it between angles of 90 and 60. So the smaller the value we get, the closer we'll be to 90, and the larger the value, the closer we'll be to 60. If the set 1 is not bigger than set 2, then we're going to map the value between 60 and 90. So smaller value is going to be 60, larger value is going to be 90. And we're going to do the same thing for set 2. So if the average of set 2 is bigger than set 3, we're going to map it between 60 and 30 degrees. And if it's not, we're going to map it between 30 and 60 degrees for that top servo motor. After that, we're going to wait 30 seconds, and then we're going to read new photoresistor values by setting EQ to false. And what that's going to do is let us know if we need to move the bottom servo again or the top servo. So we'll scan for new values. And then here we have a move servo function, and this is in charge of moving these servos. So we're going to take a target angle in, and then we're going to read the current angle that we're at. And then if the current angle is not equal to the target angle, we're going to step in the right direction until they equal each other. And then we can write the current angle to the serial monitor.